In the previous video, we calculated and visualized MandelBrot sets using only Excel's formulas. Now we're going to give ourselves a break and make things a bit easier by allowing ourselves the luxury of using macros. This will make every step along the way easier, be it dealing with complex numbers, executing the recursive calculations, or visualizing the results. As was the case with the formula-based implementation, there is no real business need to create MandelBrot sets using as ineffective of a tool as Excel to do this. Instead, the motivation for taking on this challenge is that it serves as a nice intermediate learning opportunity for Excel's macros and Visual Basic. Doing this will require us to utilize a broad range of macros functionalities without needing to go very deep into any one of those. For example, we'll be needing to create custom functions, utilize looping calculations, and automating and formatting changes of cells and tables, all of which is cumbersome or impossible to automate using only formulas. But as we will see, this is really easy for macros. I will be assuming that all of you are familiar with what the MandelBrot set is and how it's calculated and how it's visualized, as in this video we'll be jumping directly into the execution part of the work. In case you need a refresher on what MandelBrot sets are, please refer to the previous video which I've linked in the description. So let's get this thing going. As we learned last time, there are three main complications when seeking to calculate and visualize MandelBrot sets using Excel. While we were last time able to overcome these complications using only formulas, today we will see how macros will make overcoming every one of these complications much easier. For dealing with complex numbers, we can set up new simple custom functions that do the needed calculations without us needing to retype the formulas again and again. The needed iterative calculations are a breeze when we can use the loop structures instead of needing to overcome the calculation logic and template for recursive calculations. Visualization will be faster to calculate as we don't need to have thousands of active and heavy formulas. This will help us get results faster and create higher resolution pictures. Since the task at hand needs multiple steps, let's draw a quick and dirty flow diagram to illustrate our game plan and the needed modules so that we don't get lost along the way. Ultimately, we're aiming to build the top-level macro called MandelBrot, which collects user inputs on what part of the MandelBrot set the user wants to visualize and in how high a level of a detail. Then it evaluates all the starting points inside this visualization area and calculates the number of iterations needed to escape beyond the radius 2 circle. Finally, we want to remind ourselves what were the exact inputs we used to calculate the results so that we can more easily tweak and fine-tune our visualizations later. But we do not make this one top-level macro to be one massive lump of code. Instead, we want to break it into smaller chunks that we can build and debug more easily. Additionally, breaking this up into smaller parts will give us a nice training example on building and deploying custom functions and building and calling sub-macros. The first sub-element that we will be needing is the visualization grid in which the calculations and visualizations will take place. We will be using the same principle as we did with the formula-based execution, that is, using Excel's cells as pixels to visualize the MandelBrot set. We will be creating this grid using two inputs collected from the user, which tell us how wide and tall the visualization area needs to be. The cosmetic gap in this game plan is that it requires a small bit of external information in addition to the inputs provided by the user. This external information are the conditional formatting rules needed to tell Excel what color it should apply to each pixel based on the number of iterations needed to escape beyond the radius 2 circle from that pixel's starting point. I've spent quite a lot of time trying to get rid of this gap via color scales or hexadecimal calculations, and while those approaches worked and allowed me to make this top-level macro independent of external data, I did not find the results aesthetically pleasing. I might be making a separate video on this adventures into color scales and hexadecimal calculations, but they would be sidetracking this video too much as we would be focusing or wanting to focus on the MandelBrot set. For today's needs, we'll be using the conditional formatting approach as it is very simple. It only takes a few minutes to do and provides us with full and easy control over the visualization. Next, we need to be building the function that evaluates how many iterations of the x squared plus c calculations it takes to escape beyond the radius 2 circle. We want to be able to provide the start point coordinates to this function, and in return, this function should provide us with the number of iterations needed to escape, or 0 if the iteration results never begin to explode, no matter how hard and how many times we crank up the iteration loop. Finally, we need to build a couple of simple sub-functions to streamline our work. First, we need a function to calculate a complex plane point's distance to origo using Pythagorean formula. Secondly, we need a pair of functions to iterate what are the next iteration's real and imaginary coordinates, given the original start point and the previous iteration's coordinates. And with that, we're done. Even though this might at first look quite intimidating, especially if you're only getting into macros and Visual Basic, all these parts are eventually really simple. The functions, loops, and the formatting we are using, they require only a handful of lines of code each. I know that this code could be streamlined a lot and make it shorter and even faster, but I've opted to prioritize the ease of reading and being able to understand what each part is doing. With that said, let's whip out Excel and begin working on this.
So let's begin building this bigger macro by having first this kind of a sub-elements, smaller sub-elements available, meaning these functions and this sub-macro, so that we can then build these top-level main elements based on those immediately. So first of all, we need to be kind of starting here by creating this grid, which is the idea is that we would have this sub macro that we tell it that how wide and how tall the grid should be, and then it just creates the correct size, meaning transforms the size of the Excel cells into pixel sizes, and then adjusts the zoom, and then brings the conditional formatting to that grid area. So the desired use case would be that the user would be just opening up a new sheet and then launching the macro. And then the macro would be asking some inputs from the user, and based on those inputs, it would start creating this grid. So now we need to first try to figure out that what kind of commands could be used in macros to do this formatting on this sheet. So instead of just going to some libraries and trying to find what are the correct command codes, so the easiest way I found to find the correct commands is to just make a test macro that just records what you're doing, and then copying and pasting that information for your own purposes. So first of all, let's just record ourselves a test macro that reveals what are the correct commands that we should be using. So first of all, just make sure that you're using the use relative references, and then just start recording. Okay, and now the macro is recording. So the idea is that since we would be feeding this sub macro the grid size, meaning how far to the right on the real axis and how far down on the imaginary axis would be needed. So it would be going to the bottom right and then selecting all this area. And after this selection would be done, then it would be just readjusting these sizes, heights and widths of these cells to make it correct size for our purposes. So this is the first step. So let's see where we are right now, and then let's continue from there. So, okay. So this is already giving us plenty of good stuff to copy with pride. So in our own macro, we will be wanting to provide this macro some inputs. so that in case we will be providing the how wide on the real axis the grid should be and how tall on the imaginary axis the grid should be. But right now, this is we were just using some random numbers in our own testing. So instead of these numbers, so the cell offset function is first kind of asking that how far down should I be going. So this is kind of corresponding to the imaginary value, and then how far right. So this is corresponding to the real value. And this is not something that we need in here. So it's selecting that cell in the correct place, and then it's kind of jumping to the left and to the up by selecting the entire area. So now we have all the grid area selected. So then what we want to do here is to change the column widths and row heights in that area. And in case we want to make this 1 pixel wide and 1 pixel tall, so the width should be set to 0.08 and the height should be set to 0.75. Don't ask me why Excel's logic is like this, but we just need to be coping with it. Okay, so let's just remind ourselves what we are doing in here. Okay, so then that's the first part done. So then we don't need this anymore. Sorry. And we need to just keep this here. Okay, so first part done. And now we need to be kind of adding more and more functionalities to this grid creation for us. So the next part, what we want to do is that we want to change the zoom of this slide so that we can have more pixels visible in our screen. So once again, let's record. Zoom, and then let's just go make the zoom a bit smaller, and then we can stop it, and then go into edit. And we can find that the correct command that we should be using is neatly in here, and we can just pick that here, and then rest of this is irrelevant for us. Okay. Next, we want to kind of go to the styles sheet and fetch the correct styling, formatting styling, and then bring that to here. So let's then shift to absolute references and start recording yet another test macro for us. So first of all, we need to be going to styles sheet, selecting the sheet where we have the conditional formatting set. We need to be copying the formatting and then coming here and pasting it here. Okay. So once again, let's see what did that give us. Okay. Okay, so first of all, it just tells that we should be going to the styles sheet, selecting the cell A2 and copying whatever is the form in that cell. Okay, that we can bring here. And then what we are doing then is that we are coming back to the original sheet. We are selecting the area where we have the grid, and then we are doing the copying or pasting the formatting in here. So we are pasting formats. Okay, so actually we don't need the other stuff yet, because the point is that we want to be making our macro independent of the name of the sheet that we are on. So we want to be able to come back to any sheet and for this we need to be kind of changing our macro a bit in the beginning so that we can remember what's the address to return to. So for this we need to be specifying a new variable called start sheet name, and this is just a string. And then okay, and then instead of coming back to sheet number 2, we come back to start sheet name. Okay, and then about the area that needs to be selected, so we just can reuse this stuff in here, and then pasting the formatting to that area. And with that, we are done with our first sub macro. But still, before going forward, so let's make sure that after we have done this grid creation, we just come back to the top left of our sheet so that we can continue doing the rest of the stuff from the correct start point. And that's it. Okay, then what we need to be doing next is that start building the rest of these kind of complementary elements. And this means that we'll be needing to build these custom functions that we can use in the rest of the kind of creation. So this is nothing more complicated than just creating a few really short new functions for us. So let's start first of all by creating this function to calculate the distance from Origo. And the idea is that we will be just feeding this function some coordinates of real and imaginary axis, and then it would be providing us with a result about how far from the Origo that is. And the result is, let's use single as the data type. So this should be making the calculation a bit lighter because it doesn't have too many unnecessary decimals. And this function is really simple. So it's just using the Pythagorean formula. So and that's it. Our first function is ready, and the rest are not more complicated either. And the next two functions that we need are for the iterating the next real axis coordinate and next imaginary axis coordinate using a slightly different formulas. So and for this we need to be providing a bit more starting information. So we need to be telling that what was the original starting point and what was the previous iteration's coordinates. And that's it. Then very, very similarly, we need to be creating a similar function for iterating the imaginary value. And that's it. Now we have the kind of a small new sub functions ready. So now we are in a situation where we have built these smaller supporting functions so that they will be making our work later on much easier. And now we need to be moving on to building this iteration function that basically tells that when we feed it some starting point coordinate, it just provides us with the information that how many iterations does it take to escape beyond the radius to circle, or that it gives us a 0 in case the escaping never happens, and that we can classify this starting point to be inside the MandelBrot set. So let us start building this function. And that we want this output to be of data type integer because we are only counting how many iterations does it take. So, but for this function to work, we need to be specifying a few more variables so that they can operate properly. And then we need to be setting up the kind of a function to operate properly. So in the beginning, we want these iterations to start from the given starting point without overriding this starting point information. And then we want to set up the escape speed so that that in case this does not change in any of our later work, then we can just kind of have some value assigned to it that we can interpret that it means that the escaping never happens, and that we can assign this point into the MandelBrot set. Okay, and then we need to be kind of starting to build the iterative calculation function. And for this, because we need to be having a control that how many times these looping calculations happen, because we don't know whether they're going to spontaneously end ever. So we need to be using the for loop to do this. And we need to be selecting that how many times do we want to use it. So I've just selected that the maximum amount of iterations that I want to try is 40. So once again, you can use bigger or smaller numbers, but I found 40 to be plenty enough to give good and high quality pictures. So then we need to be kind of checking that every time we kind of do this loop, that what's the distance where we are currently. And here we are using the function that we already built here in the previous part, so that it's just using the Pythagorean formula to calculate the distance for us. Okay, and then we need to be just checking that is this starting point already beyond the radius to circle, so that we don't kind of keep cranking up the for loop for unnecessary reasons. And then in case this happens, we don't need the rest of the for loop, so we can just exit ourselves out of there. But if not, then we need to go to the actual heavy work. And here we are using this iterate next real coordinate and next imaginary coordinate. And that the reason why we need to do this kind of a temporary real action, temporary imaginary coordinates is that if you would be directly assigning that the next new real value would be coming out of this function, then the when we would be kind of needing the previous iteration's real axis value, that would have been already overwritten. So that's why we need to have this kind of a bit convoluted intermediate step of assigning this temporary coordinate values. But then once we have those calculated, now we can then overwrite the previous iterations coordinates. And then we need to be checking that now that we have these new coordinates, does this bring us beyond the radius 2 circle? So that in a case we encounter that, yes, now we have found the iteration that brought us beyond the radius 2 circle. So just pop out the counter where we were at when that happened and just stop doing the rest of the for loop. And then ultimately, when all this is has been done, then we just need to be kind of popping out the result of our function. So the result needs to be having the same name as the function. And that's it. So this was the kind of the heaviest work that we will be needing and doing in the entire work of calculating and visualizing the MandelBrot set. And now I think we should be done with this one. So we are nearly there. So the only last thing for us left to do is to build this top level macro that pulls all this together and utilizes the smaller sub elements that we have already created. So let's do the final sprint, shall we? So we need to be creating a macro called and for this macro to work, we need to be specifying a couple of variables to work with. So we need some information or placeholder variables where we can kind of use to specify what is the location of the visualization area that we want to draw, and then what is the size of the grid that we want to apply to that area. Next, we need to be asking user to provide us what are the values that the user wants to assign to these values. And for this, we can use input box function. And similarly, as we did in the formula-based execution, we also need to be calculating that what's the increment of moving from one pixel to the other. Okay. So basically the logic is that we want to see that how long of a distance on the real axis we want to cover, and then divide that by how many steps we need to be using to cover that distance. And after this, we need to be kind of starting to set up the problem or this iteration so that we can start going through this visualization area pixel by pixel, calculating that what is the coordinate on that pixel, and then feeding that coordinate to our iterations to escape function, and find out that what is the number or the number of iterations that should be filled to that coordinate. So for that, we need to be, first of all, starting by calling the create grid function so that we have this grid where we can do the rest of the step. And after that, we need to be starting systematically going through this grid from the top left corner. And since we are using a couple of additional variables, so let's just make sure that we have specified placeholders for those as well. Then we need to be going through this grid row by row, and for this we need to be having two embedded for loops. So the one for loop goes individual rows, and then the other for loop goes the individual columns, and together they go through every single cell that we have in this visualization area. So we need to be specifying that what is the vertical or the imaginary coordinate of the row that we are currently working on, and that we can get by just starting from the topmost row and then going down as many times as we have been kind of going through this row counter, and decreasing the height by the amount of increment that we have calculated. And then we need to be, when we are within that row, we need to be going through each cell or column of that row one by one. And for this, we need the other embedded for loop. So the logic of finding the correct coordinate of the column where we are on that individual row. So it's just that we start from the left, and depending how many times we have kind of moved on towards the right, we just add one increment at a time. And then once we are in that cell, we need to be doing the business where we are actually doing the entire thing. So we need to be feeding these coordinates of the cell that we are currently in to this iterations to escape function that we built earlier on, and whatever is the value that this function gives, we just write that or fill that to the cell where we are currently. And after we're done, we need to be just moving on to the next cell to the right of this on this row we're currently working on. And then once we have gone through the entire row using this for loop, then we need to be going to the next row and doing it once again. So basically going down one increment and then going left as many times as we have been kind of doing this column counting. Okay, and with that, I think we are starting to be quite ready for our first attempt of seeing whether we get any results or not. But let's just make a couple of small adjustments, because we are using a couple of more variables, this row counter and column counter. So let's just make sure that we have those specified in here as well. And now we are ready for the moment of truth. We're actually testing that whether or not our macro works. So let's see. We are now on the new sheet, and let's see that we try running our macro. Okay, so let's try something really small in the beginning. And we have a problem. Okay, of course it doesn't work. So let us then debug. Okay, and the first problem was that I forgot to remove this parentheses. So when I input this start sheet name, I don't need to have these in here. Okay, so let's then try again. Okay, yet another problem. So okay, so we have been in also having here as a for loop where we have been utilizing a variable that we have not set up previously. So let's just add this in here, and let's then try again. And it seems to be doing something. Let us see. So we seem to be having a success. We have our first proof of concept that our macro is working, and it's drawing us a MandelBrot Set visualization. So of course this is just a really small one, but it's just showing that everything is working nicely. But then let's see if we would be able to go beyond this minimum viable product, and let's see if we can kind of improve how this is working. Okay, and the first thing that I would like to improve on this is that since finding and locating the correct place where we want to focus and what we want to visualize in the MandelBrot set is kind of a iterative work. So I would like to be kind of reminded that what were the parameters that I used for creating this particular picture so that I would be able to tweak and tune them for my next attempt. And I think that the best way or place to kind of put those parameters would be in the kind of a bottom right of this picture, because in here the row heights of these pixels are just 1 pixel, and here are also 1 pixel, so that the first area where we have these naturally sized pixels where we can actually read what's written on them is in here. So let's just print the parameters and the selections that we have been inputting in here as a reminder for ourselves. Okay, let's see how that would change the outcome. Okay, so this seems to be working nicely, and we keep getting kind of a reminded that what was the parameters that we use for this so that we can tweak and tune them later on. But then kind of as therapeutic as it is to kind of see with your own eyes where the picture is starting to appear. So I think that let's see that if we would be able to make this drawing of the picture a bit faster. So first of all, let's just kind of set up a way to measure how long it takes for us to draw this picture. So we have a baseline and we can continue to see that whether we can find some improvements upon it. And for this, we would need to be kind of setting up some kind of a timer to measure that when this calculations begin, when do they end, and how much time did we spend on actually completing the entire macro. So we need to be specifying a couple of more variables for us. And we need to be selecting that when do we want this timer to start. So I think that the best time would be after the user has provided the inputs and then the automated procedures start. So that would be a good time to kick off the timer. And then the good time to end the timer would be when the outer for loop has finished its job. Okay, and then let's put the result of the processing time somewhere here as well. Okay, let's see if this works. Okay, do we have a typo? End time. Ah, yeah, of course. Time end. Okay. Okay, now that we have set up ourselves with this baseline time of 121 seconds to draw this relatively small 100 by 100 MandelBrot visualization. So before kind of cranking up this picture and resolution to bigger sizes, so let's see if we can kind of optimize this to be something a bit smaller. So typically the best way to optimize this kind of a visually macros that provide some visual result is to just disable the screen updating so that it only shows the results after the picture is ready. So let's see how much that would be helping us. Okay, and the results are quite dramatic. So we have an improvement from the previous time of 121 seconds to a time of 6.6 seconds. So that's quite good results for just one line of code. So I think we are now ready with this optimization, and we can start utilizing it and playing around and see that whether we can find some nice structures and visualizations in this MandelBrot set. Okay, so let's try to do something similar that we did already in the previous version when we were doing the formula-based implementation. So trying to uh, drill down into this topmost bulge of this biggest cardioid that the MandelBrot set has and see that what kind of structures can we get popping out of there. So let's see if we can find that one. Okay, so immediately I noticed that our parameter information has gone missing. So we have some kind of a problem in our macro. So let's go and fix that. So where do we specify the location of it? Okay. So the problem is here because the offset function first asks that how much down do you want to go, and only then how much right do you want to go. So this should be the other way around. So that's settles that hopefully. But then it seems that I would want to have a bit less of horizontal distance and bit more of the vertical distance, and then a bit more also towards the up. So let's try finding a new version of this. Okay, starting to get there. So let's fine tune this one more time before cranking up the resolution. Okay, I think we are now ready to crank up the size of the picture to see that what does this area of the MandelBrot set look like in closer zoom. And finally, one eternity later, we have our result. So it took about 20 minutes of processing time to create this 1000 by 1250 pixel picture that consists of 1,250,000 pixels in total. So let's see what does it look like in closer view. So, as you can see, there's quite a lot of fine structures coming out of the MandelBrot set, but then when you really start to look more closely, you can start to see that the granularity is starting to disappear on the very finest structures in here. So in case you would want to have a ability to drill deeper and deeper into these MandelBrot sets, you might want to specify or build a macro so that it does more than the 40 iterations per pixel before concluding what color it has. So possibly you wouldn't go all the way down to 100 iterations or so, but at least with this relatively top level drill downs into MandelBrot set, this 40 iterations is able to provide us with quite nice visualizations of the structures of the MandelBrot set. So, with that said, I think we are now officially done with drawing MandelBrot sets using Excel. And in the next coming videos, we'll be doing something else that has a bit more direct business relevance and practical applications.